In my last lecture, I started discussion of load characteristics and load management. Okay. So, I discussed the electrical definition of load, and I also discussed different types of loads. Then I also discussed this load characteristics or load curve. Okay. So, we have different types of load curve, which include residential, commercial, industrial. For residential, commercial and industrial customers. Now, so I think I stop at this point where I discuss this load factor. Okay. So, load factor is one of the indices which is used for modeling electrical load. Okay. And as I discussed in my last lecture, it is a ratio of the average load to the peak load demand or maximum load demand. Okay. So, load factor is always less than 1, why it is so I discuss. Next I will talk about in my today's lecture is the coincidence of load, okay? Coincidence of the load. So, as you know that load whenever we are talking about is not load demand of a particular customer. Okay? So, load we are talking about is the aggregated load demand of a group of customers, of a number of customers. Okay. So, for example, under a distribution network, suppose this is my substation, then we have a suppose single feeder coming out from the substation, which is supplying a number of loads like this. Okay. Now, each load is basically this arrow is signifying that they are connected to the load via a distribution transformer. Now, under a distribution transformer we have a number of loads connected, okay, and each of the load is having their individual load curve or individual load characteristics. Okay. So, when we take the load curve under this feeder, that means this is basically the aggregated load demand of all these customers, okay, whoever is connected to that particular feeder. Okay. And when we will talk about this aggregated load demand, there exists certain diversity or certain amount of coincidence of this load demand. This behavior, this coincidence behavior we will be trying to understand in this particular lecture. Okay. Now, as I said, so load behavior at the distribution level is dominated by individual appliances characteristics. Okay. So, even in a under a particular residential customers, we have different appliances, and all these appliances have their individual power characteristics. Okay. So, they have individual power characteristics. Okay. So, we will be trying to understand this their coincidence or diversity. Okay. So, all customers, as you know, do not have their peak demand of electricity precisely at the same time. Okay. So, they do not have this peak demand at the same time. You may understand that one load characteristics is somewhere like something like this, another load characteristics can be something like that. So, this peak demand occurs maybe at different time of the day. Suppose this for that particular characteristics peak demand occurs at 6 p.m. For this characteristics peak demand can occur at 11 a.m. Okay. So, we do not expect that all the customers will have same peak demand and they occurs at the same time of a day. So, there exists certain amount of diversity. Okay. So, this needs accurate load studies, and also we should have proper measurement and proper measurement infrastructure, and also for a proper modeling approach in order to understand this diversity among the different loads. Now, I have in this particular slide I gave an example to show you how this individual load characteristics would be different than the aggregated load characteristics. Look at this figure which is drawn in the left hand side of this slide. It is basically power demand or load curve of the entire residential area having a number of customers. N cus is basically a number of customers. You can consider this as 100 or 200 or whatever. So, this is the load characteristics or power demand characteristics of a residential area, where we have a number of customers connected. Okay. Now, this load curve obviously the aggregated load demand, the aggregated load curve of all these 100 or 200 customers who are there in that particular area. Okay. And suppose this load characteristics is something like that, load characteristic, this is power demand and this is the time of the consumption. Okay. So, this shape of this load characteristic is something like that. Here we have one peak which occurs in the morning, here we have another peak which occurs in the evening. So, this is morning peak, this is evening peak. Okay. And of course, this morning peak is the higher than this evening peak, and this is the maximum demand or peak demand of that particular locality or particular residential area. Okay. Now, the question is, this is the aggregated load curve of this number of customers. Now, can we determine the individual customer characteristics from this aggregated demand, or rather can we scale down this aggregated load demand characteristics, and a scale shape of these characteristics will represent this individual customer characteristics. Can we do so? So, this is the question. That means, here in this figure, in the right hand side figure, whatever is drawn is basically a scaled load curve, okay, which is scaled down by number of customers. So, which is scaled down by 1 upon n number of customers power demand from, that means, this represent 1 upon n number of the overall aggregated load curve. So, the shape of these characteristics will be same as that of these characteristics, because this is nothing but a scaled characteristics of the aggregated load demand. So, that is why means maximum demand will be 1 upon number of customers. So, this is where maximum demand occurs, and this magnitude is 1 upon this peak demand of this aggregated load characteristics. Now, the question is, do we get individual load characteristics exactly scaled version of this aggregated load demand? So, that is why I set a question here, can the load curve of individual customer be drawn by scaling down of the aggregated load characteristics? Answer would be certainly no. Okay. So, it is not possible. So, if I show you that how would be the individual load characteristics, you can understand. So, let us see that how would be the load curve of a customer looks like, individual customers. So, if you look at this characteristics is of different shape than the aggregated load demand of that particular area. Okay. So, these characteristics, if you look at, it is basically looks like a needle peaks, a number of needle peaks, and it a sorted of discontinuous type of load curve, sorted of discontinuous. So, at the certain moment of time, load demand suddenly increased and it comes down almost instantaneously. Okay. So, this is how this individual characteristics may look like. So, individual characteristics of a customer load demand cannot be derived from this aggregated load curve just by scaling down this load characteristics. This is not possible. Okay. So, if you look at this, what it should look like, the scale version of load curve, but this is the actual load characteristics, okay, which is completely different, not only the shape of the characteristics, but also the pattern of the consumption. So, individual load characteristics would be completely different than the aggregated load curve. This is you have to understand. So, if I write the essence of this point that we are trying to establish here is that individual load curve of a customer is completely different than aggregated load curve. So, this one has to understand. So, although means this particular customer is part of this aggregated load demand, but its individual characteristics may be completely different. Okay. Now, here there is an illustrative example that if we have number of customers aggregated, how this aggregated load curves will look like. So, in this figure you can see when we have two homes, two residential homes and their load demands are aggregated, then the characteristics will be like this. Now, when we will have these 5 numbers of homes, each of having a residential customer and you aggregate their individual demand, the characteristics will be like this. Okay. So, this is an illustrative example, does not mean that every time it has to be same only. But when we aggregate this load demand for 50 homes, you can see the how would be the characteristics, and also when we will aggregate this load demand of 100 residential customers, this is the aggregated load characteristics. So, if you look at the difference of these 4 characteristics, then you will understand that. So, they are not only different in view of the shape of the characteristics, but their consumption entire this load curve it gets smoothened when we will increase the number of the customers. So, if you look at this when we have 2 number of customers, when we this aggregated load demand characteristics almost similar to what we got in the individual load characteristics, individual customers load curve. But when we aggregate 5 homes and 50 homes and 100 homes, you will see this characteristics becomes more or less smooth like this, and it will get a similar kind of characteristics that we got in previous slides, that is these characteristics. Okay. So, the moral of the story is that with the increased number of characteristics, with the increase in number of customers, the aggregated load curve becomes a smooth characteristics with a aggregated load curve. The characteristics becomes smooth. Okay. So, even though in individual load characteristics are of needle shape with occurrence of this individual load demand almost instantaneous, but when you will aggregate these characteristics will be almost smooth. Okay. Now, why it happens? Why it happens? This happens because of the diversity of the load. This happens because of the diversity of the load. Now, what do you mean by diversity? Diversity is that it is a parameter because of which all these customers consumption pattern are identical. Okay. So, there exists certain amount of diversity and there also exists certain amount of coincidence. Okay. Now, we have certain indices to measure the diversity of this load demand. Okay. Now, before we go for this indices, we have a definitions of diversified demand and non coincident demand. Now, okay. Now, a diversified demand is the demand of the composite group as a whole of somewhat unrelated load over a specified period of time. What does it mean actually? Suppose I have a group of customers or group of loads having 100 different types of loads and we are aggregating that. Okay. Now, when we will get a aggregated load curve of all these 100 customers or 100 loads, the peak value or the maximum value of that load demand would be the diversified demand. Okay. It represents the diversified demand or demand of a group. Whereas, there is another definition which is non-coincident demand, which is sum of the demands of a group of individual load with no restriction that interval to which each demand is applicable. Okay. If I give an example, then things will be clear to you. Suppose we have 3 loads. Okay. So, we have 3 load curves, that means, we have 3 load curves. Now, from these 3 load curves, let us find out the peak demand of individual load. Okay. So, the peak demand of load 1, for load 1 peak demand is, let us say 10 kilowatt. Okay. Now, for load 2 peak demand is, let us say 15 kilowatt. Okay. And for load 3 this peak demand is 20 kilowatt. Okay. So, these are the peak demand of individual load curves. These are the peak demands of individual load curve. Okay. Now, when we aggregate all these 3 loads and we will get a aggregated load characteristics, okay. And for this aggregated load characteristics, peak demand is, let us say 30 kilowatt. Okay. For aggregated load characteristics, what do you mean by aggregated load characteristics? When we aggregate these 3 loads, you will get a composite aggregated load curve, and for that aggregated load curve, the peak demand is, let us say 30 kilowatt. Okay. Now, this 30 kilowatt is basically representing this diversified demand, because it is the demand of this group or demand of this composite group. Okay. So, this 30 kilowatt is the diversified demand or group demand, and this non-coincidental demand is basically the sum of this individual peak demand, which is equal to 45 kilowatt. Okay. So, this 45 kilowatt is basically representing the sum of this individual peak demand, and most likely they are non-coincidental. That means, they do not occur at the same time, as I mentioned various times. Okay. So, it may so happen this for load 1 peak demand occurs at, let us say 10 a.m. and for this load 2 peak demand occurs let us say 11 a.m. whereas, for load 3 peak demands occurs let us say at 3 p.m. But ultimately, when we will aggregate these whole characteristics, it may so happen this for aggregated load characteristics, the peak demand occurs at 7 p.m. Okay. So, that is why we are calling this is that non-coincidental demand. Okay. So, sum total of this individual peak demand which are non-coincident to each other is basically called as non-coincident demand, whereas this when we will aggregate all these individual load characteristics, that peak demand of this aggregated load curve is representing that diversified demand. Okay. Now, look at how this regional diversity exists in Indian load characteristics. Okay. I again sincerely acknowledge that I took these characteristics from POSOCO India. Okay. Now, if you look at these 4 characteristics, where this W are basically representing western region load curve, western region of this country, which include these western states Gujarat, Maharashtra and those states. Northern NR represents the load curve of northern region. SR represent this load curve for southern region, which consist of these states in the southern part of this country, and ER basically representing the eastern region load curve. Okay. Now, mostly as I have shown you, this western region, northern region and southern region, their load demands are somewhat close to each other. So, that is why for representing this load characteristics, their demand profile is shown over in the same scale. Okay. So, their individual load demands are somewhat similar. Okay. Whereas, in eastern region, the load demand is almost 1/3 of these 3 regions. Okay. And that is why for eastern regions, this scale is different and it is in right hand side of the characteristics. Okay. Now, this although this characteristics is of 8 years old, that is it was taken on 30th January 2013, but you can get an idea that how this regional diversity exists in a country. Okay. Now, if you look at this characteristics for western region, this is the western region characteristics, this is basically the characteristics for northern region, and the bottommost one this blue characteristics is basically representing southern region. Okay. So, they have some individual load demand they are basically aggregated load demand of a particular region. Now, if you compare these characteristics, what things you can understand? First of all, this let us see the western region. You can see there are 2 peaks, one is during morning peak, which occurs between 10 to 11, and there is an evening peak which occurs somewhat at in between 7 o'clock to 8 o'clock. So, this is the evening peak, and both the peaks are almost of same value. Okay. This is for western region, and since it is in January. So, evening peak or residential demand is somewhat less, because we do not in January it is the winter season for this country, and during that time we do not have this air conditioning load. Okay. So, somewhat evening demand is lower, and morning peak and evening peak are almost identical. Okay. Also, this happens because of that in western regions we have many industries. So, their morning peak is considerably high, and it is almost identical to the evening peak. Whereas, if you compare the load characteristics of this eastern region, these characteristics, you will see there is a huge difference of this evening peak and this morning peak. This morning peak somewhat occurs between 9 to 8 to 9 or 9 to 10 during that time, and it is somewhat in a order of 1250 multiplied by 10 to the power 3 megawatt, and this evening peak is almost several or almost if not double, it is almost some factors of this morning peak, and there is a huge difference between this evening peak and morning peak, and evening peak is much higher than this morning peak for eastern region. Why it happens actually? This happens normally because eastern region we have less industry. So, industrial demand is not much, and that is why morning peak is not much higher. So, this region characteristics is mainly dominated by this residential area, commercial areas, and that is why during evening this load demand is much higher. Okay. Similarly, this northern region also there is we have industrial areas. So, we have almost similar morning peak and evening peak, and southern region also we have certain industries, also agricultural demand is there, and that is why it is having almost similar characteristics as that of these other 3 load demand. So, the essence of the story is that we in the different regions we have different types of loads, and that is why there exists diversity. Okay. And this because of that, you know, their characteristics are of different. Okay. Now, we have certain indices to study. One is called demand factor. Demand factor is the ratio of maximum demand of the system to the total connected load. Okay. So, demand factor is the ratio of maximum demand to the total connected load. Okay. It means that if I give an example that let us say in a particular room, we have a number of appliances. Okay. We have some appliances for lighting purpose, or we can call them as lighting load. Okay. And let us say for lighting load it has let us say 150 watt. Okay. For fan, let us say we have 200 watt. Okay. Some computer we have whose rated value of this power demand is somewhat 200 watt, and so on. Okay. Now, if we have this particular three types of loads in a particular room, so the total connected load demand would be equal to the sum total of individual rated capacity. So, it will be equal to 0.55 watt. Okay. But it does not mean that every time we are using all these appliances simultaneously. Okay. It is very rare that we use all these appliances whichever we have in a particular room or in a particular house. Okay. So, what we do, we suppose plot this load demand characteristics of this room, and eventually we get this maximum or peak demand is somewhat 400 watt. Okay. Then our demand factor will be equal to, so this demand factor will be equal to 400 divided by this total connected load, that is 550, then whatever value is there. Okay. So, generally this demand factor is lesser than 1 unless your peak demand coincides with your total capacity, which is very rare. Okay. So, demand factor is calculated in that way. So, it is representing a factor or ratio of this peak demand to the total connected load, or the sum total of the rating of all the appliances that we have. Okay. Now, there is another index which is called diversity factor. What is this diversity factor? Diversity factor is the ratio of the sum total of the individual maximum demand, that is the non-coincidental demand which we are talking about, and it is the ratio of this non-coincident demand to the diversified demand or maximum demand of the whole system. Okay. So, if I go back to this example that I set here, suppose we have this 3 load demand, we have 3 different loads and they have their individual peak values written over here 10 kilowatt, 15 kilowatt and 20 kilowatt. If you sum up then 45 kilowatt will be equal to this non-coincidental demand or non-coincident demand, and this 30 kilowatt is basically this diversified demand or the demand of this group. Then according to this example, the diversity factor will be equal to, its numerator is non-coincident demand or sum total of this individual peak demand, that is 45 kilowatt, and its denominator is the peak demand of the group or the diversified demand, which is equal to 30. So, this is 45 by 30. So, this should be greater than 1. Okay. So, diversity factor is a index which is normally greater than 1. Okay. It can be equal to 1 under what condition, when your aggregated peak demand exactly equal to this sum total of this individual peak demand or non coincident peak demand, which is very rare. Under that scenario only we have this diversity factor equal to 1, but other than that diversity factor would be equal to would be greater than 1. Okay. So, it is the index whose value would be greater than 1. Okay. So, it basically measures that how much diversity we have under a aggregated load. Okay. So, whatever I mentioned there already I have shown with the example. So, diversity factor is the ratio of the sum total of individual peak demand or non coincident demand to the diversified demand. So, denominator is the diversified demand or demand of this group, and numerator is the sum total of individual peak demand or non coincident demand. Okay. So, next index is basically the utilization factor. Next index is the utilization factor. It is the ratio of maximum demand to the rated capacity of a system. So, normally utilization factor is basically similar to the demand factor. It is the ratio of maximum demand to the rated capacity of the system, and normally this utilization factor is used to understand that particularly transformer is utilized, a particular transformer capacity is utilized. So, it is the ratio of peak demand or maximum demand to the rated capacity. Okay. Now, we can also calculate this diversity factor in terms of this demand factor, So, what we can do? You can see this diversity factor is written as the sum total of individual maximum demand divided by the diversified demand or the group peak demand. Now, this individual maximum demand can be written as that individual demand factor with multiplied by total connected load. So, this peak demand is replaced by this demand factor multiplied by total connected load, because effectively this demand factor is equal to this peak demand divided by total connected load. So, peak demand is basically replaced by here demand factor multiplied by total connected load. So, we can find out this diversity factor in terms of this demand factor as well. If the demand factor is known to us for individual customers, and if this total connected demand is known to us for an individual customer, we can calculate or compute this diversity factor from this demand factor and total connected load. Okay. Now, I have an example to show you a numerical example. Okay. So, look at this numerical example. We have a typical power distribution network. Okay. So, this is the substation, this is the substation bus, from which we have different number of feeders. So, this is suppose feeder 1, F 1 stands for feeder 1, F 2 stands for feeder 2, F 3 stands for feeder 3, and F 4 stands for feeder 4. Okay. So, we have 4 number of feeders under a substation. This is the substation which is connected to the sub transmission line or transmission line, and there is a transformer in between to step down the voltage level. Now, only this a part of this feeder 4 is shown over here, only part of this feeder 4 is shown over here. This feeder 4 is having two lateral feeders, one is this lateral feeder, another is this lateral feeder. Okay. One is this lateral feeder and this lateral feeder. So, there is a nomenclature, this L 41 stands for this first lateral of this feeder 4. Okay. So, L 41 stands for this first lateral of this feeder 4. Similarly, this L 42 stands for the second lateral of this feeder 4. So, here 4 represent this, that this is a part of this feeder 4, and this 2 represents that this is lateral number 2, lateral feeder number 2 of under this particular feeder. Okay. Now, under this lateral 2 of this feeder 4, we have a number of distribution transformers. So, this each this black dot is representing one particular distribution transformer, to which we have a number of loads connected, So, here other distribution transformers are not shown over here. Here one distribution transformer is shown over here, which is connected to 6 number of customers. Again, this DT stands for distribution transformer. This 4 basically represents that it is at feeder 4. This 2 basically representing that it is part of this lateral 2, and 7 is representing that it is 7th number of node. Here you can see 1, 2, 3, 4, 5, 6, 7. So, it is at 7th number of node. Okay. So, this distribution transformer is at 7th number of node. Okay. Similarly, customers are also numbered as 4276, 4275, 4274, 4273, this one 4272, and this is be 4271. Okay. This is not a very standard nomenclature, but this is one of the means way that you can represent a typical distribution network. Okay. So, this 4271 is basically representing one particular customer, which is at feeder 4 at lateral 2, it is at 7th number of distribution transformer, and it is its customer ID is 1. Okay. So, similarly 4276 is representing it is at feeder 4, it is at part of this lateral 2, it is at 7th node of this particular lateral feeder, and it is customer ID is 6. Okay. All right. So, look at this problem then. We have 6 residential customers, and each customer number is specified as the way I mentioned. 4276 means the first digit stands for this feeder, that it is a part of this feeder 4. Then second digit stands for it is that at what lateral feeder it is connected. So, it is connected to the second lateral feeder of this feeder 4. Then the third digit is representing that it is connected to the distribution number of the 7th node, or it is the 7th distribution transformer to that particular lateral feeder, and 6 is the customer ID, okay, or house number or customer ID, whatever you can say. Okay. Now, it is mentioned that assume that connected load is 10 kilowatt per house. Okay. For each house this connected load is same, and that is for 10 kilowatt. So, this is this connected load is 10 kilowatt, here also connected load is 10 kilowatt. Similarly, all these for customers connected load is 10 kilowatt. Now, what do you mean by this connected load? This connected load, as I discussed few slides before, that it is basically sum total of all this rating of the individual appliances that that is there in that particular house. Okay. So, if we have a number of appliances in a particular house, just just take a sum of their individual rating, individual wattage or power consumption rating, then this will represent this summation will represent this total connected load. Okay. Now, the demand factor is also given for this house, it is given as 0.65, and the diversity factor for this group of the 6 load 6 customer is also given as 1.1. Okay. Now, what we have to do? We have to determine the diversified demand of the group of this 6 house under this transformer DT 427. So, under this particular transformer, what would be the diversified demand? Now, what do you mean by diversified demand? Diversified demand means suppose all these customers they are having individual load characteristics. For example, the 6 customer they are having some individual load curve, this is power demand, this is time. Then we also have different load curve for all these customers, we have power demand to the time. Now, if you sum up, if you aggregate all these load characteristics, then you will be getting some aggregated power demand characteristics, and let us say this will be something like this. this will be something like this. This is your P demand and this is time. Now, when we aggregate all these characteristics, so this is the power demand of the, or we should directly write is as a load curve, aggregated load curve. Now, this diversified demand is the peak value of this aggregated demand. This peak value of this aggregated demand is asked to find out, provided that they provide you this data of total connected load, that is 10 kilowatt, this demand factor as 0.65 and the diversity factor 1.1. Okay. So, how can we solve this? Is that a difficult problem? It is not difficult problem at all, okay? Because many information is given to you. First of all, you know this connected load and also you know this demand factor. From these two, what you can determine? From the information of demand factor and the connected load, which information you can determine? Because you know that demand factor is the ratio of peak load demand, individual peak load demand and to the total connected load. So, if this demand factor is given, so if you multiply this demand factor with this total connected load, what you will get? You will get the peak demand of all these customers and they are identical, it is mentioned they are identical. Okay. So, peak demand of all the customers are identical, but it may not occur at the same time. Okay. So, what would be that peak demand? So, peak demand you can find out simply by multiplying this that demand factor with this total connected load. So, which will be equal to 0.65 multiplied by 10, that is 6.5. So, basically the peak demand of individual customers is you can find out from this demand factor and total connected load. So, it will be 6.5 kilowatt. Okay. Now, once you get that, then the sum total of this individual peak demand or non coincident demand, which is the numerator of the diversity factor, can be determined. Okay. So, this will be equal to sum total of this all this 6.5. So, this will be nothing but 6.5 multiplied by 6. So, once you get that, that will be the numerator of the diversity factor, that will be the numerator of the diversity factor, and the diversity factor is given, that is 1.1. So, from that we can determine the denominator of the diversity factor, and that denominator is eventually that diversified demand or the demand of this group. Okay. So, let us see how it is solved over here. Okay. So, the way I was talking about, first they determine that, as we know, this diversity factor dVF is equal to sum total of this individual maximum demand with this diversified demand of the group. DGR is representing this diversified demand. So, this is representing this diversified demand, which is nothing but the peak demand of the aggregated load curve, which is nothing but peak demand of aggregated load curve. Okay. Now, again we know that this individual peak demand can be written as that demand factor multiplied by total connected load. Okay. So, it is given that n is equal to 6, n is number of customers. Okay. And their individual demand factor dF, here dF stands for demand factor and dVF stands for diversity factor, and this you have to understand. Okay. Now, individual demand factor is given as 0.65 and dVF, that is diversity factor, is given as 1.1. Okay. So, from this demand factor and this total connected load, we can find out that individual peak demand, which is equal to 0.65 multiplied by 10. Now, as we know that this peak demand is same for all these 6 customers. So, you simply multiply with 6 in order to find out the summation of individual peak demand. Okay. So, this numerator will be 6 multiplied by 0.65 multiplied by 10. So, this is the numerator of this DBF, and DBF is given as 1.1. So, we can determine this diversity factor of this group, which is equal to this value divided by this diversity factor, that is 1.1, which is coming out to be 35.45 kilowatt. So, this is a very simple problem given to you. Okay. So, in that way we can solve this small problem for this load, composite load characteristics. The problem is not much difficult at all. So, here many information is given to you, here demand factor is given to you, total connected load is given to you. So, you can find out the individual peak demand, and this individual peak demand is mentioned as identical for all these 6 customers. So, the sum total of this individual peak demand will be total number of customers multiplied by this each of this individual peak demand. So, which is 0.65 multiplied by 10, that is 6.5 kilowatt multiplied by 6, and this diversity factor is given as 1.1. So, you replace this this denominator with this diversity factor, and you can find out what is the value of this diversified demand of this group. Now, this value, this 35.45 is basically representing this peak demand of this aggregated load curve of all these 6 customers. So, when we will individual customers peak demand is given as 6.5 each, but when we will aggregate them, this would not be exactly equal to 6 multiplied by 6.5, because these individual peak demands do not occur at the same time. Okay. And that is why you can see that aggregate diversified demand or the peak demand of the aggregated aggregated load is basically equal to 35.45, which is not equal to this value, that is 6 multiplied by 6.5, which is much higher than this 35.45, and that occurs because of that the diversity of the load demand, that occurs because this individual although these loads are having some identical demand factor and connected load, but their consumption, this pattern is not same. That means, at the moment of when customer 1 is having this peak demand, at that same moment customer 2 may not have this peak demand. Okay. That means, all these individual customers, they have different timing for consumption of the peak demand, and that is why when we will aggregate their individual peak demand, this would not be equal to this peak demand of the aggregated load curve. Okay. So, this is the main thing that you should understand, and that aggregated load curve we determine from this diversity factor. Okay. So, with this I will stop at this point and we will continue on the next day. Thank you.